So, good morning, everyone. My name is Francisco, and today I will talk about the exploring the days quark matter under strong magnetic fields. This is my outline of my talk. So, the theory responsible to study the strong interactions are called by quantum chromodynamics, and the quantum chromodynamics is responsible for studying one of the fundamental forces of the nature. We have the gravitational force, electromagnetic force, weak and strong force. And the particles from the standard model of the particle physics responsible for this interaction are called by quarks and gluons. And the quarks are inside of the proton and the neutron. And the difference between a proton and neutron is the configuration of the quarks. While the proton has two quarks up and one quark down, the neutron has two quarks down and one quark up. Also, the quarks have the electric charge of the elementary charge. So the quark up has 2/3 of the elementary charge, and the quark down has -1/3 of the elementary charge. This fact explains the reason about the proton has a positive charge and the neutron hasn't charge. So the quantum chromodynamics has two important properties. The first property, color confinement, where the quarks have three color charges during the strong interaction. There are the charges blue, green, and red, and this confinement says that the force between the quarks and the gluons don't decrease when they are separated. This is the opposite, for example, of the gravitational force. Another property is the asymptotic freedom, where this property says for us that the nuclear reactions that involving high energy, or in other words, quarks and gluons, when they interacting very weakly, cause the quark-gluon plasma. And in 2004, this property, or this theory, gave for three physicists, Poynter, Wilczek, and Gross, the Nobel Prize for this discovery. So, here we have the phase diagram from QCD, where this diagram shows for us the possible phases that the quark matter can have. So the relation between temperature and density, we have the summary regions about these quantities. So when we have low temperature and low baryon density, we have the hadronic phase. In other words, the quarks and gluons are inside of the protons and neutrons. When we have high temperatures and high density, we have the quark-gluon plasma. And my interest in this graph is to study the low temperature and high density, and also to try and understand the effect of external magnetic field in this graph. Because large magnetic fields are created in particle accelerators, and its value is about 10 to power of 19 Gauss, approximately. And other object of my interest is stars, because these objects develop on their surface strong magnetic fields of the order of 10 to the power 15 Gauss, and even bigger inside, 10 to the power 18 and 20 Gauss. And certainly the magnetic fields affects the phase transition of quark matter. So we study the dense quark matter. We will use the effective models, in this case Nambu-Jona-Lasinio model. This model was proposed in 1961 by Yoshiro Nambu and Giovanni Jona-Lasinio, and the Lagrangian density of the model is given by equation 1. And the Lagrangian density of this model will give for us all the dynamics from the quark matter, where in the equation 1 we have C that represents a spin order of the quarks, U and D. Tau are the Pauli matrices, del mi is a covariant derivative, Q is a charge matrix, F mi is an electromagnetic tensor, and G is a constant coupling of the model. So from the Lagrangian density, we can obtain the thermodynamic potential given by equation 2, where in the equation 2 we have the effective mass given by capital M, and we have 2. Alpha K is a Degenerate factor summed over the K index. A is a total energy, which depends of the electric charge of the quarks, magnetic field, effective mass, momentum in the lambda levels. And the thermodynamic rotation will give for us all the thermodynamics of the quark matter, the dense quark matter in this case. So we can separate our thermodynamic potential in contributions: the vacant contribution, medium field contribution, and only magnetic contribution. The vacant contribution is given by equation 4, and the only magnetic contribution is given by equation 6. So now to obtain the limits of the temperature goes to 0 of the thermodynamic potential, we have to the following calculation Matsubara summation given by equation 8, and according to this result, we can establish the half contribution given by equation 9. So this way, by performing the integration, we get a result in an analytical expression given by equation 10. Okay. So in the equation 10, we have SF, which depends of effective mass, electric charge of the quarks, magnetic field, and lambda levels. And the maximum number of lambda levels is given by equation 11. So now we have the complete thermodynamic potential given by equation 12, only with effects of density and magnetic fields. So in terms of thermodynamic quantities, we must find the effective mass given by equation 13. This is the gap equation. And after that, we can find the equation of states. The equation 14 is a pressure. The equation 15 is baryonic density, and the equation 16 is energy density. My pressure is normalized in this case, given by equation 17. So my parameters in this work that I use are in the table. The value of the cutoff of my integrals, lambda, the value of current mass, M0, the value of a coupling constant, G, and the value of pion mass. So my results here, we have in the left side, the potential thermodynamic potential in function of effective mass for different values of chemical potential. And we have a global minimal in 400 for the value of mass. And when we have an increasing of the chemical potential, the global minimum goes to between 0 and 100, the value of mass. And the right side, we have the relation between effective mass and the chemical potential for different values of magnetic fields. And we have, in this case, a Brachis-Carroll symmetry, because the increase of the chemical potential made with the decrease of effective mass, in this case, for different values, of course, of the magnetic fields. So here we have in the left side, the relation of the effective mass for if the magnetic field for finite value or potential chemical equals 0. We have the increase of the mass. This is called in the literature magnetic catalysis. And the right side we have the same case, but for the finite values of chemical potential. And we can see some oscillations, and these oscillations are called as the Hans-von-Alphen effect in the literature. The same case occurs for the baryonic density in function of magnetic field for a finite value of chemical potential. In the left side, we have some oscillations, physical oscillations. And in the right side, we have the value of baryonic density in function of chemical potential for different values of magnetic field. And we have also some oscillations in this case. So in the final, we have the normalized pressure in function of chemical potential and energy density in function of chemical potential for different values of magnetic fields. And when our pressure arrives in chemical potential, critical chemical potential, it starts increasing. The pressure increasing when we arrive in critical chemical potential. The same occurs for the energy density. But in energy density, we have some oscillations. So, my conclusions of this talk is that the role of magnetic field effects in the quark matter is of the great importance. The consequences of the Landau quantization are not negligible for high values of magnetic fields. When we have a chemical potential equals 0 and a magnetic field not equals 0, we have the magnetic catalysis. When there is an increase in the magnetic field, the number of Landau levels for a given energy is reduced. And then I'm making a famous oscillation called the Hans-von-Alphen effect. And the perspectives for the future are directed at the nucleotron-based experiments ion collider facility in the Russia. When they are in the operation, we will be able to compare our results of the effective models, such as the NGL model or Nambu-Jona-Lasinio model. Thank you for your attention.